This is a second of 6 related videos on modeling and testing simple permanent magnet DC motors. In this video, I'm going to talk about modeling of the motor and characterization using the common torque speed curves, and use that curve to relate to key specifications that you can look for some of these motors. So the motor torque speed curve shown here, so it's plotting torque, output torque versus speed, and it's this curve here. And there's 2 key specifications. The stall torque is the torque at 0 speed. There's also a stall current at in that condition. There's a no load speed that's also important, typically considered the top speed when there's no load, right? And then there's a no load current for those conditions. Normally that current is overcoming internal losses. I've overlaid on this torque speed curve a load curve, so you can envision that this might be the motor, say, driving a load, say here, and this load itself might have this characterization. The torque could be linearly related to the speed in one case. In the case shown here, this is the slope BL. So one way that we use torque speed curves is to overlay them this way, and then where they intersect, that gives you basically a solution, right? You have 2 equations, 2 unknowns. You can solve for the operating torque and speed for that motor, the intersection showing that operating condition. Keep in mind, this is a steady state characterization of the motor. The motor itself might have dynamics, or it might be operated dynamically. In those cases, we might take into account dynamic effects that I'll talk about shortly when we look at a model and the derivation of the torque speed curve and what it does not include. This slope for the slope B sub m here is for the special case, say, where you might have linear losses, and in that case you could come up with that slope by just taking 2 measurements, a stall torque and no load speed, and that would give you that slope to characterize very quickly a simple motor of this type. A lot of motors that we've talked about in a related video, different types, have different torque speed curves. For example, a shunt DC motor, where this shows resistance, but also the field inductance could be in parallel. You might have a very different type of torque speed curve. Note that the torque here is on the abscissa, right, on the x-axis, if you like, versus the y. Very common to see that in manufacturer specs. Also compound motors or split series or series motors, where you have the field being excited. Remember, these are different from the permanent magnet, where the field is supplied by stator mounted, say, permanent magnets, where we commonly will see sort of these linear characteristics. Again, manufacturers might give you these specs, and that might be all they give you, and so you can use these, as we discussed in the previous slide, to understand performance by overlaying load characteristics as well. Here's an example of a very small little toy motor. This Mabuchi motors, I'd say the size here is about 1 inch, and very low power. You can see about not even a half a watt. Take a look at this characteristic here. This is actually plotting torque on this axis versus, and the speed is here. It's kind of hard to read, but that I think is RPM. And so you can see that the torque speed curve is, torque speed here is linear here, right? This says stall torque is something like 1.86, and the units here are milli-newton meters. A very small motor. But again, a lot of times you need to gear these motors to get sufficient torque. These are very high speed, like this 7,500 RPM, so you really gear those down to get that torque up. Compare that look at all the information that they provide. Even though this is a very cheap motor compared to this other motor that we're going to be using in the lab, say, you might just get something like, well, here's the voltage range you can use. At rated voltage of about 4.5 volts, it'll turn at 90 RPM. Gear ratio is about 1 to 48. So in those cases, you might want to do some testing, figure out maybe how to better model the motor. You might fully test it to get a torque speed characteristic so that you can better design for performance and so on. And that's what we're going to be doing by building a basic model. So here's what a simple permanent magnet DC motor looks like. Sometimes we'll have inductance as well as motor inertia representing the rotor. You might have some internal losses here shown linearly with B sub m. The torque generated by the motor ideally, remember, is Rm times Im, Rm being this motor constant. This Vm is the back EMF. V sub S of t here is the input voltage. So we're going to simplify this, start off just by looking at the electromechanical conversion. Again, we've discussed these equations before. You get torque related to current, right, through the torque constant. You also have back EMF related to the speed through that same constant. Sometimes you'll see different constants here. If you use SI units, then Rm always has units of either Newton meter per amp, or in this equation here, it's equivalent to what? Volts second over radians. So volt seconds per radians is exactly Newton meter per amp. You could show for SI units. Sometimes you'll see non-SI units and different units based on applying the motor more simply, like might be given in RPM or might be given in inch pounds and so on, English units. But if you stay with SI, then you can use the same constant for both cases. I'm showing the bond graph version and also sort of an electrical mechanical schematic here. I'll use the bond graph here in the next slide to build up a model. Keep in mind that that little ideal power conversion says that the power in is equal to the power out. It could, whether you have a generator or motor, right? This action is equal. There's no energy stored. We're only accounting for the pure electromechanical conversion, and we use that as the core of the model. So here's a model where we've taken out all the energy storage. So there's no inductance, no inertia. So this is a model that's useful for steady state operation and for characterizing the torque speed curve. Here you have an input voltage, right, at the motor terminals. I mean, I'm keeping some linear resistance of the coils. Here's my EM conversion relation. The back EMF is implied. Torque, I'm including a gear ratio here. Some of these motors are going to have that. Little typo here. This should be omega sub m. This is the output of that gear ratio. And here's a bond graph. All right, let's use that bond graph to derive torque speed curve. I'm going to go ahead and apply causality on here for those of you who know bond graphs. If you don't, the relations are on the next slide. But I'm going to input voltage here. I'm going to have to make an arbitrary causality assignment on the load. I'm going to assume that the load specifies flow, or that I want my motor to be specifying torque as an output, speed as an input. So this is an arbitrary assignment. It means I'm going to get an algebraic equation because I have what's called an algebraic loop, if you know bond graphs. That algebraic equation is, of course, our torque speed curve. We're going to deliver torque as a function of speed. That speed, velocity flow goes across that transformer, specifies the flow on this one junction. So those two bonds have effort implied. Across the gyrator, that gives me effort on this side, which means that this bond has to have the current specified into that one junction. So what this is saying physically, right, is that input voltage, back EMF, gives me current, right? That's what the resistance does. It's basically specifying how much current is flowing through that motor armature at steady state. All the dynamic effects have gone away because you're now running at steady state. It's just losses that are basically describing how this motor performs. The bond graph can be used to derive the equations, right? The equation that I'm interested in deriving is, of course, this torque here, which is I want to get that torque knot here. So torque out rather, and that's the gear ratio times this tau, which is the difference, right? Tau sub m, this torque, minus tau sub bm, right? So that's where I start my torque speed relation. And that's what I do on this slide here. That's the relationship. Now I had I need tau m, right? So tau m is now from the basic EM conversion. Im is Vn minus Vm, which is the back EMF here, divided by Rm. Substituting that relationship for back EMF, then the motor delivers basically, as I said above, Tm minus tau Bm. So my output torque is that gear ratio times that difference, right? So that's this relation here, right? This is tau sub m minus tau sub Bm, okay? Substituting those assumed relationships for those motor elements. Substitute all that in there, you'll get a torque speed curve that looks like this. So it's the gear ratio times all this quantity here. You have recognized this here as the stall torque, right? And then you have, this is the slope of the basic torque speed curve, but note that it's changed by the gear ratio on the output side of the gear ratio. If you don't have a gear ratio, just make that equal to 1 and you have that. And make omega 0 equal to omega m here, right? But I'm basically looking at the output of the motor through the gear ratio, okay? This relationship, if you have these quantities now, r sub, little r sub m, big R sub m, and b sub m, you can basically quantify this torque speed relation as a function of whichever speed you want, either the internal motor speed or the output motor speed. And this should give you the same kind of relationship that we've seen in those other torque speed relationships on those slides. So how do you interpret this? Well, all this is doing is plotting, again, output torque, and I'm showing here versus speed, but this could be output speed as well, right? Depends on what you want to plot here. This slope, again, depends on whether you're including the gear ratio or not. If you want to plot it as a function of motor speed or output speed, it depends again what you want to do. Note, depending on what input voltage you give, that's going to determine where you start off this curve. So for the input here being at the rated voltage, you're going to have that green line. As you increase that input voltage, let's say you go to V3, all it's going to do is shift, right? All it's going to do is shift this torque speed curve. The slope's going to stay the same. It's just going to shift it up higher. If you drop the voltage, it's going to shift it up lower. So that's the basis for controlling basically the performance of most of these motors. You're just going to be modulating, if you like, the input voltage, and you're just shifting this curves up and down, and you can handle different curves, as I'll show you in a second. Right? So they're always going to move parallel to each other. Again, as long as all those internal losses are linear. Okay. So, for example, let's say I'm running this with a pulse width modulation. So the input voltage is some pulse width modulation times some battery voltage. This is sort of similar to what we do in the lab. Let's say I connected remember these are load curves that you could show on here. I'm showing a load curve that's just a constant, like that. Okay. So I have a constant torque that I'm driving using this motor. And what I'm going to do is just change the voltage. And you can see that as I change the voltage, each of these curves shifts up. So I get different operating points for each voltage, right? And if you just drop those values down here, that gives you the different speeds for different voltage. And that's all that's happening when you operate this motor at different input voltages. Remember, each of these dots also represents a operating point. So at this guy right here, this torque TC2 times omega 2, right? That's the power that would be delivered, for that condition. Okay, I'll show you how to use a torque speed curve and why we find it useful. In the next video, we'll talk about experiments to determine this model parameters for these torque speed so that we can populate this torque speed curve.